physicist who wants to study the effective field theory on the surface of the black hole. This black hole is an ideal target for study. Its isolation makes it a clean, uncontaminated sample for observing quantum and relativistic phenomena.
It has been a long time we are on this journey, and also it is going to take another 1,000,000 years. Some generation needs to do this. We are a few light years away, no danger for us. We can now be seen as a hovering observers. We are far and constant with respect to the black hole.
We know the spacecraft will be lost, but our goal is to capture as much data and imagery near the event horizon as possible.
Sagittarius A star is a supermassive black hole at the center of the Milky Way galaxy, and sometimes we underestimate the role of this black hole in our own existence. But this black hole shows itself in X-ray and the radio wavelength, but if we also look at the motion of the stars around it, in the long term we can see the huge gravitational impact on the motion of those stars. Supermassive black holes are one type of black holes. We also have stellar black holes in the Milky Way galaxy. For example, Cygnus X1 is one of the first candidates for the black hole. The strong X-ray emission is caused by falling of the matter into the black hole in the binary system. But today we don't want to talk about complicated phenomena around the black holes. We want to talk about why black holes are like holograms of information. The concept of the black hole was proposed first by Carl Schwarzschild during World War I. He found the solutions to the Einstein equations of general relativity to see how a massive object can distort and change the space-time around it. From the equations, he concluded that if the object is squeezed enough in a small region, it would create a gravitational boundary around it that no information can get out of that boundary. At the beginning, they were skeptical about that, and there was no known mechanisms to explain how a black hole can form. In the 30s, Chandrasekhar found that if a white dwarf exceeds 1.4 times of the mass of the Sun, it cannot resist against the electron degeneracy, and it would turn into a neutron star. 1 decade later, Oppenheimer and Volkov found that if a neutron star exceeds 3 times of the mass of the Sun, no known force can stop the collapse. So at that time, we know that how a black hole can form from a massive star. Basically, anything can be a black hole. It depends how much we squeeze it with any mass that it has. Black holes have very wide ranges of sizes. They can be very, very small and quantum mechanical, and they can be very, very large, and based on the general relativity, you can explain them. But the point is that it can connect these two extreme physics to each other. Very, very small and very, very large. But also let me add these laws of nature. It's a made-up word from myself, but it is a principle that we think the laws of nature should have, like symmetry, causality, and consistency. Symmetry is probably very important because a lot of people like it, some people don't like it. But however, it's an important part of physics. Like in quantum mechanics, we have time reversal, and that means that we can always reverse the time direction, and it works. It's a physical process. But in thermodynamics, we don't have the time symmetry, so certain flow of the energy is not allowed if the entropy goes down in an isolated system. Well, since the beginning, the gravitational object and gravity was always against the second law of thermodynamics because it tends to squeeze everything into a singularity. So the question was, to what degree a black hole obeys the second law of thermodynamics? Does it have an entropy or temperature? And these are the questions that are answered in the 60s and 70s. '60s and the 70s have a lot of signatures, but for black hole physics, it was a golden decade. One of those people who had a lot of good ideas at that time was Roger Penrose. He worked on the singularity formation in the black hole, and he also proposed the idea of censorship, which means the black holes can keep the information that it is fallen into them. The other one was Penrose mechanism. You send a particle inside of the orbit of the black hole and it decays, and the final particle that comes out of the orbit has more energy than the initial particle, so we kind of extracted energy from the black hole. So black holes were not just untouchable objects, but they are like a membrane that they have extension into a region of space that you can extract energy or maybe information out of them. The mystery of the black hole thermodynamics was solved by Bekenstein. He asked the question, what will happen if two black holes start to merge and form a bigger black hole? It is so easy to write down the GR equation of the black hole, and you will see the sum of the areas of the two black holes is smaller than the area of the merged black holes. It just came out of the GR equation and triangle inequality. But Bekenstein said, wait a second, the entropy and the area are very similar in this context. So then if you define the entropy as a coefficient of the area and then as a function of mass, you can use basic thermodynamics to take a derivative of mass with respect to entropy and define the Bekenstein temperature. Bekenstein temperature is the temperature of the black hole, and it shows black holes obey the second law of thermodynamics and they have well-defined temperature. If we think the area of the black holes is like entropy in the thermal systems. Another interesting thing is the relationship of the size of the black hole with the temperature. So bigger black hole has lower temperature and a smaller black hole have higher temperature. That's why you shouldn't be worried about the small black holes, because they evaporate very fast. But anyway, the question was that if the black holes have temperature, then they must radiate. But how? The answer to this question was given by Stephen Hawking in 1974. In his paper, he said that black holes can emit particles such as neutrinos, photons, electrons, and everything. But the reason is that the event horizon is different from the rest of the points of space. Event horizon is like a one-sided street. The concept of pair creation in quantum field theory now comes handy here. If you have pair creation in all the points of the space-time, so if any pair is created, one of them is going into the black hole and the other one is coming out of the black hole. This process is allowing black hole to lose energy or conversely mass. So black holes also can evaporate like any other thing. The fact that they are a thermal system and they obey the law of thermodynamics and they should evaporate like any other thing. Hawking's argument was that the observer at the infinity at rest with respect to the black hole can send a perturbation to all points of the space-time and see the response back. But in infinite time, the observer can distinguish the event horizon because he has to test all the points. It would get longer as it gets closer to the event horizon. Hawking radiation encodes the quantum correlation or quantum information of the black hole on the horizon. As we said, it is revealed to the observer at infinite time, so it is not just like going up the black hole and see the Hawking radiation instantly. It basically takes forever. The event horizon actually is a global feature of space-time, means that all the observers at infinity, they can see an effect like a sink in all of the points of a space-time distorted by the sink. But this is not a local phenomenon, which means that if someone is free falling into the black hole should not see the event horizon. So if you start to free fall to the black hole, the event horizon gradually is gonna fade away. This can make a paradox because the observer at the infinity at rest does see the event horizon, while the infalling observer cannot see that. The other paradox is that the observer at infinity at rest doesn't see any information get into the black hole actually because of the asymptotic time dilation, because of the GR equation. So someone at infinity sees the object near the horizon is frozen completely and doesn't go in. But the person who is free falling shouldn't feel anything special about entering the horizon, or they don't see a horizon at all. So they can go in, but the person who is standing outside sees them to be frozen near the horizon. Now this is how the paradoxes start to form. If you don't see anything goes inside, then the outgoing Hawking radiation should not have any signatures about those infalling objects. On the other word, it won't be perturbed by any infalling object. Now here is the problem, the principle of quantum unitarity. It is simple, saying that any final state should have a connection to initial state with keeping all the information in the unitary matrix or a unitary operator. So it doesn't matter what you have, a black hole or a scattering box. The laws of the quantum mechanics are symmetric under time, so you should always have to be able to exchange input and output. Which means all the information should be there. We should be able to reverse the movie anytime we want, go from initial state to final state and vice versa. So the person outside has to choose between quantum unitarity and positivism about what is actually falling into the black hole. If he doesn't see anything goes into the black hole, what's the argument? That is why Hawking had this idea at the beginning that the Hawking radiation doesn't have any signatures of the initial state. And he basically said quantum unitarity is violated. I can give you an example about the principle of unitarity. Imagine the laws of the nature are just numbers of the dice, and you have a rule about how to get to another number from the initial number. Here, for example, if you multiply by 2, take the remainder to 6 and add 1, you see that this is not a 1 by 1 rule, which means several different initial states would end in the same final sequence, so we cannot retrieve the initial state from them. On the other hand, if you set a good law, like just adding 1 to the number and cycle back at 6, you can always reverse the movie. So the quantum unitarity is something like that. The information should not be destroyed during the process. I mean, this is the whole point about physics. So some people who cared about quantum unitarity, like Gerard Tehoff and Leonard Susskind, they tried to save the quantum unitarity by proposing the idea of complementarity. Complementarity says that no observer can access both aspects of a black hole. Or you cannot at the same time be a free-falling observer and a hovering observer. Or you cannot exchange information simultaneously, or you cannot turn to each other simultaneously. But why? What is the reason? Is because there is an energy barrier between these two observers. Anytime you need to exchange between the hovering position and the free-falling position, you need to turn on the engine, and no finite amount of fuel can be used to understand all aspects of the black hole. We basically need infinite fuel, but also infinite time. So there is always energy barrier between these two observers. For example, in the special relativity, it doesn't matter if you're in the car or if you're outside. As far as the relative velocity is constant, you can change the frame of the reference without spending any energy. So that's why the person and the car are in the equal position to see the laws of physics. But a hovering observer and the free-falling observers are not in this situation, so they are not like equal. So they see different things and it is justified. There is always a barrier, an unbreakable wall between someone who is free-falling into the black hole and someone who is staying outside stationary. In the next 2 and 3 decades, Hawking was eventually encouraged by theories like ADS-CFT duality, that the information is not destroyed. ADS-CFT is stating that a physics of the boundary can be translated to the physics of the bulk, mostly by the trace of entropy on the surface and the boundary, so the entropy is behaving the same in the bulk and boundary in those dualities. But it can actually calculate how to perturb a boundary and then get the response as a Hawking radiation back. I mean, eventually physicists were able to analytically show that there are theories who preserve the information from boundary and bulk, and black holes are basically okay. They don't destroy the information, so no matter how hard the egg is shuffled and how hard the final radiation is shuffled and extremely complicated, the information is there. It is not getting destroyed, and that's the whole point of physics. In the recent years, even the idea of complementarity is challenged by new ideas like Firewall idea. It is based on the principle of quantum entanglement. So we have a principle called quantum entanglement monogamy, which means that one system cannot be entangled maximally to 2 systems simultaneously. The Hawking radiation should be entangled to itself. Why? Because the principle of unitarity is saying that if you send an entangled pair into the black hole, the final Hawking radiation should be also entangled. But the radiation at the same time should be entangled to the black hole, but simultaneously cannot be entangled to 2 objects, so the entanglement between the Hawking radiation and the black hole must be broken. The breaking of the entanglement is like breaking a chemical bond. It can release a lot of energy and heat, and creates a firewall around the black hole, which disturbs all the information who wants to get into the black hole. Now, why does it contradict the complementarity? Because based on the idea of complementarity, a free-falling object can go into the black hole smoothly and without any problem. If there is a firewall, this idea is challenged, and basically all the information that goes in is heavily disrupted by the firewall, so the black hole is protecting itself from new information to get in.